Feel free to put questions in the chat. My topic is Bose-Einstein Condensate. In the mid-1920s, Bose developed statistics for photons. However, his paper got rejected, so he sent it to Einstein. Einstein generalized it to atoms, published it, credited it to Bose. In a second paper, Einstein predicted the Bose-Einstein condensate. We dealt with fermions, which are subject to the Pauli exclusion principle, which allows single fermions in each quantum state. Bosons don't have such a rule, so they can all be in the ground state at low temperature. According to de Broglie, the wavelength is inversely proportional to the momentum, which is inversely proportional to the square root of kinetic energy v squared, which is inversely proportional to temperature. So if we decrease the temperature, we increase the wavelength of the atoms. Now they'll start to overlap each other and interfere with each other. Remember that bosons, they can all be in the ground state. And when that happens, they all form a giant coherent wave where they all march in lockstep. This is the Bose-Einstein condensate. To contain our atoms, we use a magnetic bowl where the atoms feel a magnetic force at the edges of the bowl. This is the shadow of our atoms when we turn off our bowl. If the atoms are undergoing random motion, then it'll free expand into a sphere, regardless of the shape of the bowl. But as we lower the temperature, we see a transition to an ellipse, which is an indication that the atoms are not in random motion, but rather marching in lockstep, conforming to the shape of the bowl. We're using an elliptical bowl. 70 years later, the Nobel Prize was awarded to Cornell and Wyman from Gila, Boulder, and Ketterle from MIT for creating the first Bose-Einstein condensate. This is a surface plot of what we saw before. Notice the elliptical shape. At Gila, they use rubidium atoms. At MIT, they use sodium atoms. A year before the discovery, a reviewer of Ketterle's proposal said, "This is never gonna work, but somebody has to try it, so give him the money." The Science magazine in '95, we can clearly see that the blues are the condensate because they all have the same facial expression and they're marching in lockstep coherently, like analogous to laser light, whereas the others have different colors, different quantum states in random motion, analogous to incoherent light. Now, how do we test if something is like a laser? We check for interference. So if we have two condensates, indeed, they interfere with each other, and atom plus atom gives vacuum. Before class, I made a vortex, and we can do the same in our condensate with a laser. The condensate is a quantum object, so following quantum constraints, it is energetically favorable to create many mini vortices. Now, what does this pattern remind you of? A lattice structure, triangular to be specific. It is cool how nature recreates the same pattern in different places. Well, nature is not always perfect. Sometimes it has defects. For example, a dislocation, and even grain boundaries. The study of vortices is closely related to superfluidity. When they march in lockstep, they don't elbow each other, so their flow is zero resistance. A pair of electrons behave as a boson, and they carry charge. So this gives rise to superconductivity. Like in class, if we study the spin interactions, we can study the connections between condensation and magnetism. The condensate discovery was not purely a proof of concept. It gave birth to a whole new field called ultracold atoms, or similar to how we can confine sand to specific locations using vibration, we can confine cold atoms using optical standing waves, similar to our magnetic bowl from before. If we have periodic magnetic bowls, we can simulate the electrons in a lattice with our atoms. This was coined quantum simulation. Superior to computer simulation because computers don't have the capacity to simulate many body interactions. Because we have the ability to control our optical lattice and the interactions between our atoms, whether we want no interaction, weak or strong interaction, we effectively have a dial to control how spherical we want our cow to be. And to bring us back full circle, how much detail we want in our model for our material of interest. And with that, I look forward to your questions.